Welcome to AQA AS 8.1, which is collision theory. If you need help from your textbook, then it's pages 136 to 137. So the lesson objectives for today are to understand that reactions can only occur when collisions take place between particles which have sufficient energy, be able to define the term activation energy and understand its significance, and understand that most collisions do not lead to a reaction. So here's the collision theory basics. You've done this at GCSE already, so you should be familiar with it. There isn't really anything new in this chapter, it's just a revision of what you've done at GCSE and just making sure that you're using the correct terms. So the collision theory basics are the particles need to collide before they can react. So two particles of the reactants cannot react together unless they collide with each other. So they have to collide if they're going to react. However, not all of the collisions are going to lead to a reaction. If they don't have enough energy, they'll just bounce straight back off each other and be completely unchanged, so they'll just be the reactants. In order for the reactants to turn into products, they have to collide with enough energy. And we call this energy the activation energy. Now, as well as needing the activation energy when they collide to react, they also need to be in the correct orientation to react. So they need to be in the lined up in the right way when they collide if they're going to react. And if they're not lined up in the right way, then they'll just bounce back off each other without reacting, just as they would if they didn't have enough energy. So they need to have enough energy and be in the correct orientation. So here's the official definition of the activation energy that AQA want you to learn, and that is that the activation energy is the minimum energy needed for a reaction to occur. And in brackets you can see there the official shorthand notation for writing the activation energy. So don't write, as many students do, capital A dot capital E. It's actually a capital E with a subscript A. So that's the only shorthand you can use to represent the activation energy the exam board will allow. Okay, so we can represent the activation energy on an enthalpy diagrams. You've seen enthalpy diagrams before, but you won't have seen the transition state drawn on it. So the enthalpy diagram just shows how the enthalpy changes as the reaction goes on. You can see how the reactants have more energy than the products because it's an exothermic reaction. So in exothermic reaction, remember, energy is being given out to the surroundings, so therefore you're releasing energy to the surroundings, so therefore the reactants have got to have more energy than the products. So in this case, the reactants have more energy than the products. However, in order to make the reaction go, you need to put some energy in, and that activation energy, as we said, is represented by the symbol EA. And on this diagram you can see we've written a transition state. So a transition state is somewhere between the reactants and the products. So the reactants and all the reactants combine together to give this transition state, which is higher energy than the reactants and the products. And that transition state is somewhere between the reactants and products. So in order to get to that transition state, you need to put some energy in, and that's the activation energy. And then once it gets to the transition state, it will then proceed to give the product. However, for the reaction to start, you need to put that activation energy in order to get into the point where it's at the transition state. So that diagram's the exothermic reaction. We can do a similar one for endothermic. So if you look at endothermic, it's similar, except that the reactants and the products are orientated differently because the reactants have less energy than products, because remember, endothermic is taking in energy from the surroundings, therefore the products end up with more energy than the reactants. But you can see there's still that activation energy, and the activation energy goes from the reactants to the transition stage. So the last thing you need to know about this diagram is that activation energy, so the bigger that activation energy is, the more energy you put in. You have to put it in order to get the reaction to go. So if you have a reaction which is going to be slow and it's going to be difficult to get started, that means the activation energy is going to be higher. Okay, so what we need to look at next is the factors that affect the rate of reaction. And again, there's nothing here that we've not talked about at GCSE. So there's temperature, there's concentration, there's pressure if it's a reaction involving gases, there's surface area, and there's presence of the catalyst. So we'll talk through each of these individually quite briefly. So temperature, if you increase the temperature, then the particles have got more energy, which means that more frequent collisions are going to occur, and there's also going to be more successful collisions occurring. Because if they've got more energy, they're going to be moving faster. If they're going to be moving faster, then they're going to collide with each other more frequently. And if they've got more energy, then when they collide, you're more likely to have a successful collision, which is just our way of saying that the particles, when they collide, will have the activation energy and will therefore lead to a reaction. So a successful collision is a collision which results in a reaction happening. So the next factor that we need to talk about is concentration. Now, if you have a concentrated solution or a more concentrated solution, then you've got more particles in a given volume. And I've put that in a given volume in italics and bold to doubly highlight that fact, because this is a bit that students miss out in their explanations and exam questions that cost them marks. It's not correct to just say there's more particles. You have to say there's more particles in a given volume. And if there's more particles in a given volume, then that means there's going to be more frequent collisions. Because the more particles you've got there, the more likely they are that they're going to be colliding with each other. It's just like if you were in a room, the more people you've got in a room, if you're all milling around and moving around, then the more people you've got in a room, the more likely you are to collide with each other. And it's the same for particles. So pressure, this only works for gases, and it's exactly the same as concentration, in that if you've got a high pressure for a gas, that means you're going to have more particles in a given volume. And again, just like the concentration, the more particles you've got in a given volume, the more frequent the collisions are going to be. So now we talk about surface area. So if you have a large lump of a solid, then you're going to have less surface area. If you have that large lump cut into smaller lumps, then you're going to have more surface area. So the more surface area you've got, there's more places where the reacting particles are exposed. And of course, we've said that the particles have to collide with each other in order to react. So the more particles that are exposed, the more likely there is to be a collision. So you'll get more frequent collisions. So the last factor we need to consider is the presence of catalyst. So as you know from your GCSE work, a catalyst is a chemical that speeds up the rate of a reaction but isn't used up or altered in any way itself. And how a catalyst works is it lowers the activation energy. So it makes the amount of energy you need for a successful collision, it makes that smaller. So you don't need as much energy when they collide. So what this means is that more of the particles that collide will have the activation energy, and therefore you'll have more successful collisions. So now we just look back at our lesson objectives and make sure that we've reached them. So they were to understand that reactions can only occur when collisions take place between particles with sufficient energy, be able to define the term activation energy and understand its significance, and understand that most collisions do not lead to a reaction. So as usual, if you don't understand any of those lesson objectives, then either rewatch the video or have a look in the textbook or do something else to make sure that you understand it before you come to the lesson.